Hello again, everybody. Today is wrong calendar. Sorry. Wrong. Okay. Here we are. Today is the 29th of October. We are covering section 5.6. All right. And just 5.6. Okay. What is 5.6? Well, 5.6 is rational functions. And sort of again, to give you an overview of where we are, let me remind you of a couple of things. In the subject of functions, right, we are dealing with the algebraic type as opposed to the transcendental type. Of the algebraic sort, we had just gotten through the polynomial functions, or those that are polynomial based, you might say. And that would be something that basically looks like this. It's based upon, this is the building block, if you will. A term, there may be several of these, plus or minus, that the defining feature of the exponent is that it is non-negative. And it's an integer. Basically a whole number that's a positive or in theory 0. And the coefficient is real. So you may have just one of these, or you may have several of them added in sequence. And that would give you a polynomial based function. What we're doing now are the rational type. So just to draw it adjacent here. The difference is really just changing this one feature so that your building block is the other possibility. Instead of non-negative, it is specifically a negative integer. Which realistically means that it's something that would look like a fraction. Okay. And if there is a term here, a coefficient, you could either write it out in front or you could put it on top, technically. Really, the more convenient way to think of rational functions is like this. As a function that is made of two polynomial functions, one stacked on top of the other. All right. And anyhow, this is real. You could think of one as being a function, I suppose, because it is y equals 1. And then the more interesting chunk down here. But if you want to have a more complicated, more complex polynomial above, all right, and another one underneath it, this is how we generally think of a rational. Okay? All right. All right. Insofar as a graph is concerned, you have a handout already. And if you look at it here, I'll point to it. We've had this actually several times, but let's see here. Here we go. Most recently, I gave you this when we were discussing quadratics. The rational type, the most basic rational type, is the reciprocal function, right? Where it's just one above and variable x below. This is the distinct graph. These are the domain and ranges in interval notation. Anything that is a reciprocal function is going to be anything that is a rational function is going to be some derivative of this reciprocal function. That's the least complicated incarnation of this. Okay. Let me show you something. The handout that I have for you today, it's a couple of pages. Here's a summary in case you come across any weird notations. Like most of the time when we see notations, we see something like this: as x approaches negative infinity, all right, or as x approaches positive infinity. If you see the sign behind like a variable or maybe even something else, like a here, that just means that it's coming from a certain direction. As x approaches a from the left, you know, as opposed to if you see a positive behind it, it means approaching from the right side, okay? And here is an example of, again, the reciprocal function, the most basic rational, and how you could consider the curves that make up this graph. As x approaches 0 from the right, which would be from this direction, what's true about the function? The function goes to positive infinity. As x approaches 0 from the left, negative, it goes to negative infinity. That's expressing there's a dip here, as opposed to this jump upward. What's interesting about these and what makes them different from the others that we have discussed is that these famously have asymptotes. It has two, as a matter of fact. There is, usually to illustrate this, there's a dashed line, and it just so happens in the most basic type, if we're discussing the reciprocal function, I'll go with this, 1 over x. They'll use a dashed line that runs right down the y-axis. Right, it's a vertical asymptote, to give it a little distinction here. A dashed line along the x-axis, I'll put in green, that's a horizontal asymptote. An asymptote is essentially an invisible boundary. It's a place where the graph, it's approaching, it's getting closer and closer and closer to, but it will never actually reach it. If the curve of a rational, in this case a reciprocal function, the most basic type, is like this, that is signifying that it's getting closer, and this upward pointing arrow is getting closer and closer and closer to the y-axis, but it will never reach it, right? There is a boundary there, if you will, right? An imaginary boundary, it's not really there, right? It's not part of the graph anyhow. And this is quadrant 1. Over in quadrant 3 there is a similar feature of the graph approaching the the y-axis again, and it will get closer and closer and closer infinitely, but it will never reach it. Why? Because you can always have a smaller number infinitely, right? How come, I should say. Like there's 0.0, right? 1, and then there's 0.001, and then there's 0.00001. It'll get slimmer and slimmer and slimmer into infinity, but it will never actually cross or touch the y-axis, right? And this would be over in quadrant 3, technically, right? A similar thing is going on along the x-axis. As you go this way, the curve will approach the x-axis, but get only slimmer and slimmer, but never really touch it. Right? Either going towards the right or towards the left. All right. Anyhow, that is what this diagram is meant to illustrate. Okay, it's describing the behavior of these, the end behavior, essentially the arrows, from two different directions, right, and two different dimensions. One thing that's probably useful is in the most basic incarnation of these graphs, all right, there is one point that the curve does incorporate, 1, 1 in this case, and -1, -1. I say that you should probably try to bear that in mind, keep it in your mind, because when you're trying to do this by hand and maybe you're shifting something, All right, it would be nice to have some point of reference. Like most of the graphs include the origin. This is the one thing that does not include the origin. At least the one thing. Let me just pull this out. Crunching is always making it hard for me to breathe. If you look at, again, our parent toolkit functions, linear functions go through the origin. The square function or quadratic type touch the origin. All right, the square root starts at the origin. Cubic root or cube root, cubic, origin. Then when you get down to the transcendental functions, they do not actually touch the origin. All right, but the absolute value does. Those types that are algebraic, again, these 7 that we've been discussing, all right, almost all of them, with the exception of the reciprocal function, that is the rational type, incorporate the origin as a point that makes up this line or some other curve, right? The other things are that these all incorporate 1, 1 somehow. 1, 1, 1, 1, right? 1, 1, 1, 1. Just for reference, right? Just remind yourself, this type, the reciprocal, most basic type of irrational, incorporates these points, 1, 1, and -1, -1. Okay? Alright, now let's discuss domain. I don't know why I'm getting lightheaded. It's raining and I'm a little reluctant to open up the window, but I think I need it. Oxygen, yay. Swig of water. Okay. Now, because we have a function, even in its most basic form, where there's a variable in a denominator, there's going to be inherent restrictions. That is, what is allowed and what is not allowed. And for that reason, we will have to discuss domain. Okay. Now, I think I may have drawn this before, but I'll do it again. There's domain of polynomials. There's domain of what is interesting to us now, the rational functions. And then in theory, there's also of radicals. The domain, which is what x's are allowed to be, of a polynomial is basically anything in this interval from negative to positive infinity, if you're going to use interval notation, right? If you use set builder notation, they would use fancy braces, and often they would just simply draw this sort of Gatsby-esque looking R, which means all real numbers are allowed for the x values. Just to complete this thought, when we're talking about radicals, you're not really responsible for this, but in contrast, a radical would have, this is an interval in which the values are okay, 0 to positive infinity. And in interval notation, pardon me, that is interval notation. In set builder, it would look like this. What is x that is allowed? Anything that is exactly equal to 0 or something that is greater How come? Because as you know, radicals have the square root symbols, at least in the most basic type. And we are not allowed to have basically a negative onto the radical, because that would not be real. Okay? So to avoid that, this is the domain of what x's are allowed, either in interval notation or set builder notation. That's not really the subject of today, but in case you're curious, what is interesting for rational is that this is the interval. There's two, actually. What is the one number in the world that you are not allowed to have as a denominator? 0. Right? Can't have 0. In a denominator. Because that is essentially like dividing by 0. If you divide by 0, it is a mathematical impossibility. It is undefined. Right. So that limits the spectrum of what x is allowed to be. Right? And it would be this in interval notation, from negative infinity up to 0, but not including it. And then suddenly a gap, very minute, you know, if you were going to illustrate. And then it would pick up from 0, still not including it, but then run into positive infinity. And we would put a union symbol between these intervals to indicate that the spectrum of domain, that is what the x's are allowed to be, runs in this spectrum from negative infinity up to, but not including 0. And then suddenly there's a gap, infinitesimally tiny, and it runs this way. The interval notation summarizes a number line like so. Right? And you would have to use parentheses in this case. Right? Why? Because there should be a gap right where 0 is. Right. In set builder notation, it would be this. That any x is possible such that x is not equal to 0. Okay. This is really where your focus should be today. Right. Just concerned with basically the information that you see here, insofar as domain is concerned. Right. If you had a more complicated denominator than this, and incidentally, when you're considering domain, you're only interested in the denominator for a rational, really. Was primarily. You would just have to set up an equation to help you figure out what it can't be, ironically, first. A while ago, I think I said this to you, and it's still true. Right? In order to answer the question of what is allowed, you sometimes have to figure out what isn't first, because it's a much more finite list. Right? And I would suggest you work with something like this. Whatever the denominator is, right, make it part of a teeny tiny little equation. Just put a note, a cross out through the equals. This situation must hold for rational. The denominator cannot equal 0, however complicated it may be, more than just x. Remember that. Okay. You want. Here's another diagram to summarize where we're at. I have been developing this for a while, and I kind of feel compelled to turn my board sort of vertically, because I think it would fit better. So if I have to move my camera, I will. But humor me for just one moment. I hope it doesn't break. No, it's too flimsy. I probably shouldn't do this. Let's see if I can get away with using something small. This ain't work. Let me see. It's testing it out now. That's a little bit better. Yeah, this is gonna end up being a problem, so don't worry about that later. Alright, make do. Here's a diagram to summarize features of a graph. And in this case, it will be in reference to rational functions. So features of rational graphs. I had started developing this a while back. I don't mind repeating this information because it is quite a lot. Right? Now, you're probably aware at this point, especially in light of toolkit parent functions, that the basic sketch that is the basic look, if you will, is determined by the degree of x usually. It could in theory be some other letter, but let's just stick with x because it's convenient. This decides the type of function, basically. So since we're dealing with something that is rational, we can expect a graph that is some derivative of these curves, like so. And in theory, yeah, there would be a vertical asymptote and a horizontal asymptote. And it goes through 1, 1, at least to start, and -1, -1. Right. Then there are the behaviors. This is why I'm concerned with my board orientation here, because I may not be able to fit it without erasing. Behaviors. Let's spell it right. We have local behavior. And we have end behavior. The local behavior is, again, basically points of interest. And the end behavior is essentially the direction of the arrows. Okay. Of the local behavior, there's famously the intercepts. And we could always calculate, if necessary, an x-intercept, one usually, and y-intercept, which is usually just one. Now it's getting cold. Okay. Of course, you know at this point, but just for the sake of summary, when you're calculating an x-intercept, you know that you use 0 in place of y. And when you're calculating a y-intercept, you put a 0 in place of x's. It's usually the way it is. Now, insofar as the x-intercept is concerned, let me just add this. Realistically, This is the numerator that you're working with, and you'll see why later. Just the numerator. Right. You won't even technically have to worry about the denominator, but even if you did, when you're done arranging your equation, right, you'll end up with just the numerator on one side of equals. Right, once you substitute 0 in place of y. Sorry, abortic. All right. Now, you put a little squiggle here to get out of the way. That doesn't look nice. That's a little bit fancier. All right. The end behavior in the case of rational graphs is dictated by something called restrictions. Now, there are the asymptotes that I had mentioned, and I'm abbreviating just for the sake of space here. And then there's something called removable discontinuities. The asymptotes are those dashed lines, naturally, right? Let's see. And it could be of the vertical type. Or they could be horizontal. See if that's visible. Looks like it is. Does the light make it too much glare? I think it's a bit too dark. Okay. Removable discontinuities, realistically, insofar as a graph is concerned, these are holes in the picture. If continuity is something that is continuous, right, like a line uninterrupted, if you have a discontinuity, that means that there's a sudden hole in the line, all right, or the curve, right? You have to be a little careful of these. Now, I want to try to work in how you would go about figuring out these three things on this picture, all right, this diagram that I'm creating here. I'm going to end up repeating the information, but at least to give you an overview. Okay, so let's stick with this, right? If degree of the variable x is what gives you the basic shape, and the intercepts are found from inserting zeros in different places, right? In the case of x-intercept, it's the numerator that you're dealing with, right? When you're looking for a vertical asymptote, and I'll put sort of a squiggle here to separate these two, and a squiggle here to separate these two, and then dip the camera just a wee bit here. When you're looking for a vertical asymptote, sort of have this formula. You want the denominator in factors denominator and factors, which I'm purposely putting in parentheses, this was, that's usually how factors look, right? Set not equal to 0. Right? It's similar for when you're looking for a domain, right? Right. When you're looking for the horizontal asymptotes, Right? There's going to basically be 3 rules that you would follow. I'm going to go into problems to describe these, but it's the second page in this packet. These are the 3 rules. There's realistically just 2 insofar as horizontal is concerned, but you would end up having to look at these rules in order to decide the third situation. So when you consider the degree of the top polynomial, because remember rationals are made of polynomials, there's one on top and one on the bottom, one in the numerator, one in the denominator. If the top is less than the bottom, right, then this is where the horizontal asymptote is. It's basically the x-axis, because it's y equals 0. When they equal, you have to divide the coefficients. Right? The top coefficient over the bottom coefficient, and you get some number, right? Which is a y equals something. If you have the situation where the top is greater than the bottom, right, then what you end up actually is with a slanted asymptote rather than a horizontal one. And then you would really need to know polynomial long division in order to estimate, approximate a line that is a diagonal line. That would be more complicated than just y equals. It would be y equals mx plus b or something similar. Okay. That is why last time in section 6.4 we had to discuss polynomial long division because you would need it in the case of a slant. Okay. Let's see. When the removable discontinuities are not difficult to spot, but there are some technicalities, so you do have to be careful. Basically, what you would do in this case is factor everything, the top and the bottom, and then look for cancellation. If you have any factors that would cancel, instead of being a vertical asymptote, they would actually be a hole instead, if they cancel. Now there is one other little technicality, and I'll mention it now. I'll put this up here. If the multiplicity that is the exponent that is attached to a factor, usually it's represented by p, right? If the multiplicity is greater of a like factor, if you will, in the denominator, then it is still, that 0 is still an asymptote. Okay, rather than being a whole, and if you analyze it, you end up with, it would not cancel out entirely. You'd have a leftover, if you will. Right? It's only when there's a real cancellation effect, and you have to look for the cancellation before you do it, right? And realize that that would be a hole in your graph. Okay? All right. Okay. Let me just stand back for a moment. Okay. let's discuss transformations really quickly. And we'll get rolling here. We have our model for transformation. Established already, right? It is this, that a function might consist of several or all, or maybe one or two of these transformation parts, if you will. Some parts, maybe not all. Alright. What I'd like you to have is, just for our purposes now, a modified version of this. Modified to suit rational functions. And it would look like this. They're all the same jobs, right? A vertical stretch, right? Technically a horizontal stretch or compression factor, and then a horizontal shift and a vertical shift, okay? If you're dealing with something rational, what is the essence of a rational function is that it has a denominator. So if something is in the function, it would be as part of the denominator somehow. That's why I've adapted this. Okay. If you need this, use it. Right. Let's discuss an example here. You use your calculator naturally, but let's say that you were going to sketch it. This is an example function that equals x plus 2 plus 3. Sketch this by hand, just one time at least, right, so that you have a feel for it. There's two ways that you can go about doing it. Right? You could use this modified version of the transformation model. Right, to identify what is included here, what type of transformations. Or you could write an equivalent. Expression with a common denominator. You see in this case that you have basically two terms here. 1 over x plus 2 is the first term, and 3 is technically the second term. If you pretend that 3 has a denominator of 1, and that would certainly be true, right? It can be rational. Right? Then you could combine this into one term rather than have it as two separate terms. That's this. To write an equivalent expression with a common denominator, ideally the lowest common denominator. All right. Now, let us start with doing it with this modded form of the transformation model. All right. What is interesting about this blue function is that you could see that it's rational because it has these parts, right? Nothing too complicated on the top, just a variable on the denominator to make it rational. But then it has this adjacent feature, which is sitting in this position, which really is indicative of this type of transformation. What type of transformation is H? That is a horizontal shift. Similarly, this adjacent term, 3, is sitting in this position, which is indicative of that type of transformation. All right, which is a what? That's a vertical shift. Okay. So without going too crazy, I just need this space, so I'm going to erase this here. You could do this by hand. If this is the usual graph of a rational function, the most basic type, and it goes through the point 1, 1, and the point -1, -1, let us just perform these two types of transformations, a horizontal shift and a vertical shift. Do remember, the horizontal shift is counterintuitive. Right, so if you see a positive here, rather than intuitively move 2 to the right, you're going to move 2 left. The vertical shift is intuitive. It is just 2 up. 3 up. Okay. So take the interesting points here. You could apply this to the asymptotes in theory as well. But let's just deal with these points because they're sufficient. All right. If you were going to go from 1, 1 to the left 2 spaces, right, you would be headed this way, and your point would be here. Right. And then you would go 3 up. 1, 2, 3. All right. If you were going to move this point from where it is at -1, 1, -1, -1 rather, going 2 to the left would be going this way, and then 3 up. 1, 2, 3. As for the asymptotes, right? If you can think of the asymptotes as originating through the origin in both respects. Maybe I should have done this on graph paper, it'd be easy to count, right? Here's 0, 0, right? Over 1, over 2, and then up 3. 1, 2, 3. You'd have a vertical asymptote that's here now. And the other horizontal would be a little bit higher, right? Let me just go back to the origin count. 1, 2, up 3. 1, 2, 3. Yeah, I probably should have done this on graph paper, but hey, you have asymptotes like that. All right. Let me do it on graph paper just to do that. Make it a little bit easier to read. I don't want to be imprecise if I can help it. This is overkill, but nonetheless. Okay. Basic shape. Again, this is the point 1, 1. This is the point -1, -1. And if you want to take the asymptotes into consideration, that would be through the origin this way and this way. Okay. Now, if we're going to go 2 to the left to transform it, and 3 up. All right, do that to those 3 points at least. Right. 2 to the left is at -1 here, and then up 3, 1, 2, 3. One, 2, 3. This 2 to the left, 1, 2, then up 3, 1, 2, 3. Right. The asymptote, 2 to the left, that would be the vertical. And up 3, 1, 2, 3, horizontal. Right. And now you would have a graph that looks like this instead. Okay, just translated. Okay. When in doubt, you can certainly use your calculator. Let me just walk you through that real quick. Yeah. Right. If you go to y equals, we could verify that this transformation is correct. Right. If I enter the original transformation, which is that, I've got log in there, but okay. I'm going to type what you see here. I'll do it in the fast way. So 1 divided by, I'm going to use a bunch of parentheses just to be very careful. Encapsulated the first term by putting a parentheses, then in the division symbol, and I'm going to encapsulate the denominator entirely by itself. X plus 2, close that. Put a second parentheses just to represent the first term in its entirety. And then plus 3. Okay. There's a nicer way of entering this if you put, the fraction style of entering it, but we'll see if this is sufficient. Graph. Okay, and there you have it. Now it's not that enjoyable to look at. The aesthetic is kind of limited here. Well, let me just go to Z standard first. All right, here we have it. It doesn't draw the dashed lines, is the only downside to this. You could, if you wanted to, finagle the calculator to draw a solid line. All right, running this way, and there is in fact a way to draw horizontal lines this way. Just if you want to, but since it's not dashed, it might be easily confused with the axes. So I would sort of leave it alone. All right, anyhow, you can see that it's curving in the manner that it's supposed to. This all as predicted. All right. Now, if you want to just verify that the points here and here are correct on the graph, this is at -1, and then 1, 2, 3, 4, and the point here is at 1, 2, 3, -3, and then it's up 2 from the axis at least. Let's get the calculator to verify those points. All right, we can hit trace. All right, now I can enter an X value. If I type in -1, it should produce 4. Be careful, make sure that you use this button for negative, and then 4 here. Now hit enter. Oh, pardon me, I used it backwards. -1 rather, sorry. And there we have it, +4. That's where it's supposed to be. Okay, that's the point 1, 1 translated because of the vertical and horizontal shift. Now I'll just do the other one. If you go over to -3, it should be 2, and it is. Right, it's on this curve. Right. If you were to type in negative 2 right now, because it's undefined, it should just leave you out a blank y. So I'm going to just verify that. Negative 2, and you hit enter. Notice that it doesn't give you a value for y, because that is the location of the asymptote. Okay? Let me show you how to do it the other way, just in case you would prefer. That is to write an equivalent of this. All right. I'll do the work here just because I need the space. If you want to write an equivalent expression for this side of our function here, the interesting part, you would have to treat these as if they were two fractions that you are adding, essentially, which means that you would have to pretend, and it is really there, but wouldn't bother to write it, that this is 3 over 1. Right? Just to remind you, remember, when you basically add or subtract fractions, and they are glorified fractions, you need a common denominator. I like to write these vertically because I think it's a little bit easier to translate. When you're dealing with algebraic expressions, as you would be in this case, the easiest thing to do is to say, okay, that's one factor, and this is the second factor, and then just make the denominator of those two things adjacent. So you'd see that and that. Now do remember, you can get away with murder in math as long as you're consistent. If you are essentially changing the denominator here to look like this, yeah, you could distribute it, but I wouldn't bother. You would have to figure out how that affects the numerator in turn. So in the factored version of this, it's a little bit easier to see. What is it times 1 that would give you this factor times this factor? The other thing. So if in theory a person would have done this, if they would have said, well, I'm going to multiply these two things together to produce this, then I have to be consistent and do the same thing to the top. Whatever you do to the bottom, do to the top. And now just start out by putting them adjacent. You'll see this. 3 times x plus 2. You should, what you end up with at the end here, should be equivalent to what you started with. And you can see that since this is factors here and here, you cross these two terms out, you'd be left with the original thing, 3 over 1. It's legit. In the top one, if you had x plus 2 to start with, and then you ended up with this 1 times x plus 2, what would you have to have multiplied by? You would have to have multiplied by 1. So if you did that here to accomplish this, then you must be consistent to do the same thing to the top, which means that 1 times 1 is just 1. All right, let's make it red. Okay, now, once you have the common denominator, just write it like it is to start with. You only have to write it once. You're not going to combine this plus this. Just the tops get added. All right. You would have 1 from the top here plus 3 times this quantity, x plus 2. I'm going to erase this because I need the space. Right, and now you would clean it up as best you can. That is, distribute what you have to, combine what you can by adding or subtracting. If I distribute 3 to each of these two parts, then what I end up with on top is 1 plus 3x plus 6. If I distribute 1 to each of these things, it's superfluous. You really just end up with this. X plus 2 on the bottom. Combine what little you can. 1 is a like term with 6. So you end up with, written nicely, 3x plus 7 is sitting on top of x plus 2. This is the function as an equivalent. Right. If you type this into a calculator just to verify that it is legit, when it draws the graph on the one that I had already entered, there'll be no change. So I'll do that now. Here is the original incarnation of this function. I'm just going to type underneath it this equivalent here. All right, and I'll be careful. Use parentheses as 3x plus 7 divided by, do encapsulate a denominator, so I'm going to put another parentheses, x plus 2, and then close it. And now you can see the whole thing. I'll just scoot it back so that it's not obscured. 3x plus 7, x plus 2 on the bottom. I'm going to hit graph, and you'll see that it will just draw this little, this is supposed to be a clock here. It didn't change the picture as well. It shouldn't have, because that is a legitimate equivalent. Okay. What is the advantage of having this incarnation of the function versus the original one? You'll see in a moment what you could do is just zero in on the one denominator, x plus 2, and arrive at what the vertical asymptote ought to be. Right off the bat. You won't have to go digging. Okay. Only on time, an hour. Okay. All right. I'm sorry. I'm boring myself. Okay. If you just have to find the domain and nothing else of this, right? This is not at all a difficult problem, really. It's just maybe obscure, but I wouldn't call it complicated. Here's basically the process. And the domain is just a domain is just what the x's are allowed to be. In general, what you want to do is factor everything. Factor the top, factor the bottom, the numerator and the denominator. In the case of the top here, if I just wrote it a little bit nicer, there isn't anything to do really, except maybe put it into parentheses. That looks more officially factored if you do that. The denominator is the difference of two squares. It's the difference, the subtraction symbol, of two things, one of which is obviously squared, the other one can be squared. How could you rewrite 9 as 3 squared? Which means the way that it would factor is like this and this. Okay, now having done that, if you're looking for the domain, the next thing is to just zero in on the denominator. Because it's rational, you really just want to look at the factors of the denominator and set it not equal to 0. All right. You know what I should do? Let me reverse this. look at anything that may potentially be a canceled out factor. Observe any factors that would cancel. Just get in that habit, all right? If there is one, these would be holes, right? Instead of asymptotes. All right, otherwise known as removable discontinuities, if you want to be technical. Removable discontinuity. They're holes. Now, as you can see, in this particular example, there is a like factor of x plus 3 above the line and a factor of x plus 3 below the line. If you were drawing a picture and not merely looking for the domain, then you might jump the gun and go, okay, these things cancel. They do, right? But just beware that if they do cancel, right, that makes them holes, right, rather than an asymptote. Okay? Now, what we're really concerned with in this particular problem is this. We want to figure out what the domain restriction will be first. And in order to do that, we're going to set up a teeny tiny little equation just considering the domain and nothing else. The denominator. So we have this. We have x plus 3 and x minus 3 should not be equal to 0, either one of those factors. And then we will use the zero product rule. If x plus 3 is not equal to 0, we're going to find the hole. It would technically be a hole one-dimensionally. And then we're going to find this other situation here. Okay. In this instance, if you solve a little teeny tiny equation by moving 3, you would subtract 3. X would not be allowed at negative 3. Save that. So this is slightly out of the frame. And in this instance, if you move 3 plus 3, x would not be allowed at positive 3. Okay. All right. What I would do at this point, if you're making this something of a numbered procedure, is graph in one dimension. 1D, if you will. Nobody ever advertises that, right? Movies are in 1D! No, it's always 3D, get the glasses, whatever. Well, I need the space, so I'm going to just do it here. We found the two places that are forbidden, x negative 3 and x positive 3. If you were going to graph this again, one-dimensionally, right? Here's a horizontal line. That's one-dimensional. 0, negative infinity, positive infinity. Let's take those two interesting locations and situate them in respect of 0. Negative 3 would be on the left side. Positive 3 would be on the right side. And if I were going with the old-fashioned symbols of inclusion or exclusion, I would use a hole here and here. Because those are the two locations that you're not allowed to have. They're not removable discontinuities per se. Well, that one is technically. Because we're looking at it in one dimension, not two. Right? In one dimension, they're both holes. Right? In 2 dimensions, only one of them is an actual hole. You'll see that later. Right? Anyhow, if we figured out the two places that are forbidden, then what is allowed? Remember, domain is what is allowed. we ironically have to figure out what is not allowed first. That's not allowed, that's not allowed. But everything else is fine. So how would we illustrate that? We'd have an arrow shaded this way, and we'd have an arrow shaded this way. And then there was technically the space in between. Right? And if we sort of upgrade to the newfangled symbols of brackets or parentheses, since this is a whole, right, it's not included. So we would have parentheses oriented this way and a parentheses oriented that way. It's sort of like if you took a whole. Let me get my hands out of the way here. You can imagine taking a whole, right, and doing this with it. We'd have the same situation here and here, right? Last thing is, I'll put it over here. Let's write this in interval notation. Just remember, interval notation is a dumbed down picture of a graph. Right. There's an interval of what is allowed, the domain, from negative infinity up to, but not including -3. So this would be the interval from here to here. Then there's a gap suddenly in the picture. And then an interval picks up at -3 and it runs to +3. And then there's a gap. Neither of those are included in any event, and then it goes this way. I don't want this incorporated in that at all. Okay. And then you would unite these, right, by putting a U in between. This is the domain. It is a simplified number line, right, using just the interesting features, right? Where is the spectrum of answers, if you will, a spectrum of what x's are allowed? From here to here, then suddenly not, then from here to here, then suddenly not, and then from here to here. Okay. When you think about it one-dimensionally, it's often easier. Now let's say hypothetically that you drew a picture. You can. In 2 dimensions. Domain is appropriately one-dimensional, but if this was part of a graph, here's what you could do. Right? If this denominator in the style of factors cannot be equal to 0, right? And it's really x plus 3 and x minus 3 that cannot be equal to 0, right? Because of the numerator as well, being this feature of x plus 3, the thing that would have canceled is a hole in the picture. All right. The thing that got left over, which is really this one, is an asymptote. Specifically, the denominator reveals vertical asymptotes, right? Unless one of them cancels, right? Or that there's some situation where there's a higher degree in the denominator, in which case there'd be a leftover. Anyhow, let me draw this really quickly here. I'm not going to draw too complicated a graph. I just want you to see the interesting feature here. We'll do a more complicated, intricate picture in a moment. But this is thinking about the same thing, but now in 2 dimensions versus the 1. in one dimension, there's a hole here and a hole here. Right? In two dimensions, there is a vertical asymptote. This is at the location of x equals positive 3 because of the arithmetic involved. And at the location of negative 3, there really isn't an asymptote here. I'm just going to use it for the moment. All right? Our graph would basically look something like this. There's a horizontal. That's still where it is. Right. Our picture would basically have a hole here. Like that. Because it's not really an asymptote, I'm just using it for a reference. At the location of x negative 3. As you can see, it's still rational, it still has those distinct curves. I really should be more precise about where the points are, that instead of it being 1, 1, it would be something else, but you don't really have to worry about that right now. I just want you to see this is what the picture would look like. There would be a discontinuity here. Right, i.e. a hole at the location of x negative 3, the factor that canceled. Okay. And you can verify this. It's not as satisfying, unfortunately, when you do it with your calculator. You may not be able to see it, even if you zoom in, so I'll try. Yeah. All right. I'm going to enter this original function, even leaving it as 9 here. You don't have to put 3 squared, but I'm going to be careful about how I enter this half of it. Right. So the top is x plus 3 divided by, when you're encapsulating the bottom, just again remember, put a parentheses for the entire bottom. It'd be x squared minus 9. So you should see something like that. Okay, notice the bottom is sort of isolated into a parentheses by itself. There's a forward slash for division. You could enter stuff in the style of a fraction, but this is faster. So now I'm going to draw this picture. All right. As you can see, that's the same drawing. I'll put this back. Without, being very fancy. It's not precise, my graph, but the essential is incorporated here. I just put in where the vertical asymptote would be. Right. Now what you don't see, and unfortunately is in the lower curve, that there's a hole. But you could verify with your calculator via the trace feature. So a couple of things. Right. First of all, let's establish where this vertical asymptote ought to be. We had predicted it should be at the location of positive 3. So I'm just going to put in x3 and then see what it spits out. You should get no value for y, and you don't. Why? Because, how come? Because this is a vertical asymptote. Now at the same time, it just ceased to draw the graph at that location, but I'm going to put in negative 3 now. And now what you should see is that there's a hole there. So again, y, there's no value. No value. It is a little misleading, unfortunately, because if you see that this graph comes to a dead stop here, you might go, oh, that must be it. But it's not so. If you type in, let's just say, 1 extra x over to the left, negative 4, you'll see that there's a value for y. I'm going to put in -4 and now hit enter. And you have some legit value. It's very tiny, right? Again, this is going to approach the x-axis. It's just never going to reach it. So it's going to get slimmer and slimmer, right? Even if I did -5. There you have it, right? Was that 1/8, something like that? It's just an unfortunately not a very satisfying picture. You could tinker with the zoom maybe too, and maybe it will get a little bit closer. No, it's not even satisfying. In a case like this, if you wanted to get over to this location, you might choose to go through, I'm going to fix it back at standard here, 6. You might choose to use the manual transmission, if you will, versus the automatic. My calculator is going into convulsions now. You can see that it's not drawing. That happens. Sometimes it gets a little stupefied. So in that case, turn it off. Right? Turn it back on. Make it graph. And there you have it. It's okay again. It gets confused. All right. Now here's the manual transmission. Right, you could change the dimensions of the x-axis. Let's say that we just shifted this over. So instead of it going from -10 to +10x, maybe I'll make it run from +3 over to -7. So -7, and then I'll change this to 3. And hit graph. Notice it's scooted over a little bit. Again, it is unfortunately still misleading you to think that the graph comes to a screeching halt at -3. It's not so, right? And you already know. Hit trace, put in another value past that point, -4, and you indeed get a value, right? Which is not the x-axis, that would be y0. This is just underneath it. It gets slimmer and slimmer and slimmer into infinity. Sometimes the calculator is not that great, right? Okay. Now, why don't I take the opportunity, since I didn't really discuss it to this point? How did I know that in this complicated problem of this function, x plus 3 over x squared minus 9, that this is the horizontal asymptote? We hadn't looked for those yet. If I was going to draw a simple picture of vertical asymptotes, and just remembering that the curves would basically be something like this here, and in this case it just happens to have a hole. This is the cancellation effect. How did I know that this was the horizontal asymptote? Because of the rules involved. All right, now let's discuss this sheet here. Let's just consider the degrees of the top polynomial and the bottom polynomial. Remember, a rational is made of those two. What is the degree of this x, since it's the lead term and therefore would be the degree of the polynomial? If it's not written, what do you assume it is? It's 1, right? The one on the bottom is evidently x squared. Right? When your situation is that the top degree is less than, as it is in this case, the bottom degree, then this is the location of your horizontal asymptote. It is the x-axis, top less than bottom. Y equals 0, you could just say x-axis. That's how I knew it was this. Okay. All right, let me get rid of this now. And we'll move on. Collars are too tight on my shirt, because I constantly feel like it's not really that tight, but I think think it's squeezing my neck a little bit and it's making me salivate. Weird. I've always had problems with my salivary glands. I get stones sometimes. Okay. All right. Now, let's do another one that involves looking for asymptotes. Here's an uglier looking problem. It might be a little intimidating, but don't be. You're not looking for much but the asymptotes in this case. And you have to find asymptotes, both of them. And this is the problem. The function of x is equal to, just not to get it confused with the rational law here, 3x squared minus 2x plus 1, sitting on top of x minus 1. When you're looking for the vertical, versus when you're looking for the horizontal, you want the factors of the denominator only. And you're going to set them not equal to 0 because they're basically forbidden territory, if you will. So use this as a model. I hope it's not too faint. When you're looking for the horizontal asymptote, you're going to use the 3 rules. So what evidently is the denominator? X minus 1, and there's really not much to do except maybe wrap it into parentheses if you want to. So this is x minus 1 not equal to 0. If you then go about the process of solving this teeny tiny little equation, it's an inequality technically because it's not equals, right? You would add 1. And you would say, all right, x is not allowed at the location of positive 1. Now what I really should do is attempt to factor the top. But you don't really have to worry about it in this case. All right. I don't believe it actually is. To be honest with you, I didn't attempt to. I really should have verified that just because I don't want there to be some hole instead of an asymptote. But in looking at it, I don't believe it is actually factorable. No, I don't think it's going to work. You could verify that by AC product pairs. 3 times 1. 3, the factors would be 1 and 3. NBC. If I did that, I'm being geeky right now, I really shouldn't, but I want to just verify. If I split this, it would be what? It would be 3x, and it would have to be negative plus 1. And this would be 3x squared plus 1. And now I have a 4-term polynomial, which if I do that, x and 3, let's see, minus 1, and this would be plus 1, this is an x. It's not factorable, right? The reason that I can tell it's not factorable is that, first of all, these are the only 2 factors of 1 times 3 from AC product pairs to work with. That would make 2 if I arranged it as negative 3 plus 1. But when I factor by grouping, notice that one of these is negative and one of these is positive. So this is prime. means not factorable. So I really didn't have to worry about it, but I did anyway. All right, anyhow, this is where the vertical asymptote is. I'm going to draw just the vertical asymptote. At x positive 1. We have established, and I'll scoot this over just for the sake of clarity, that x equals positive 1 is forbidden, right? In this case, not a removable discontinuity, right? It is a dashed line, not a hole. This is x positive 1, okay? Now as for the horizontal asymptote, we would have to incorporate 3 rules. Utilize 3 rules. So here we have it, right? We are going to be top is less than bottom, exactly equal to, or greater. Degree. What is the degree of this polynomial up here? 2. What is the degree of this polynomial down here? Remember, it's always the lead term that decides the degree of the entire thing. Just if it's in descending order. 1. So in this situation, you have the top degree is greater than the bottom degree. Which means what? Is it actually a horizontal? No. The only situations where horizontal are less than on top, equal on top. We have this situation. This is a slant rather than a horizontal. So we need to use polynomial long division to calculate or estimate the slope, the slant. This is a slant asymptote instead. Okay, that means we have to use long division. If you can get away with using synthetic division and you feel comfortable doing that, then do so. Right? The advantage of synthetic division is that you're only dealing with the coefficients, right? But it may take some getting used to. So I'm going to do long division because it works 100% of the time. The thing on the top goes in our box here, a little division house, if you will. And the divisor is on the outside. It's x minus 1. Okay. I need the space. Okay. Now, if you weren't with me the last class, there was a handout which I will just point to for reference. In this packet, it looks like this. There is a process that describes polynomial long division, first term divided by first term, and how you would establish the other parts. If you want, and it would actually work in this case, you can instead try synthetic division, which is to use this sort of scaffolding. There are conditions that really should be met before you attempt to do that, but that was the subject of last class. Alright, anyhow, I'm going to do it this way because it works 100% of the time. This is the first term, this is the first term. 3x squared divided by x. If you simplified this, what's the quotient? 3x. Alright. I'm going to strategically write this above the thing it most closely resembles, which is degree 1, so 3x. We then have to subtract. Right? In order to establish what gets subtracted, and it will be 2 things simultaneously, I'm going to have to take this quotient and multiply by the divisor, x minus 1. if all goes according to plan, when I do that, I'm going to get something that looks remarkably similar, but not necessarily entirely. It's the first term. 3x times x is 3x squared. 3x times 1 is negative 3x. That would go here and here. This first term should match the term that's underneath. And the second one is a hit or a miss. Now, because you are subtracting two things simultaneously, as in regular long division, you have to encapsulate this, right? How come? Because you're going to distribute the negative to two terms, not just the first one. The effect is that the first term, 3 minus itself, is going to cancel out of existence. That will happen 100% of the time if you did the arithmetic correctly. All right? But be careful when you distribute the negative here. My philosophy is, remember that you have rules for integers multiplication, as that's distributing, and those for adding and subtracting, which are different. I would figure out what the sign ought to be as a result of distributing the negative first, and then cover this up. So if it's a negative times a negative, and that's what it would be, this is really a positive 3. Now, if you have one of each sign in reading these two, that dictates that you subtract them, and you end up with a positive because of the larger magnitude. The digit is just 1 technically, with an x attached to it. Then you bring down the next one, which is plus 1. And you repeat the process. This is now the first term, and you use the same first term here. X divide, you could put plus 1 if you like, but this is easier. X divided by x is just what? 1 positive. That goes up here. Okay. Then you have to figure out, again, what is being subtracted here and here, which is this number times the divisor x minus 1. Distribute, you would end up with 1 times x is just x again, 1 times 1 is negative 1. This may look suspiciously like it's going to cancel, but it's not going to, right, because of signs. This is going to be x minus 1. And if you want to put a 1 here, you can. Now, be careful, again, you're subtracting two things simultaneously, so you really must encapsulate this, like so. Insofar as the first terms are concerned, 1x minus 1x does indeed cancel out of existence as this had before. But what happens when you distribute the negative in this case? A negative times a negative is a positive. And I would purposely obscure this and then write what the outcome would be. 1 plus 1 is positive 2. What that means, since you have no other terms, is that this is a remainder. Right? So, you could put this as R2 if you like, sounds like a robot, right? Or the better way of writing it, I don't know if it would be accurate to call it elegant, or just better etiquette. Right? But here's what we have. 3x plus 1, this is the quotient up here, plus 2, and then what did you divide by? X minus 1. That would technically be the denominator of this term here. And I need to erase a lot of stuff, and I need to tell you what to do now. We did this for what purpose? We did this to determine a slant asymptote, right? That would, and since it's slanted, it's a diagonal line, right? So it would resemble this model, y equals mx plus b. And it is very similar, but it has an extra feature, right? If I just sort of superimpose this above what we just calculated, it has a slope of 3 apparently, is the x variable. There's a y-intercept of 1 approximately, and then there is this remainder. So that's why we call it an approximate. Right? Because we're going to basically, especially if you're doing this by hand, all right, without doing a brute force calculation of inserting a variable here and here, and then following the order of operations to figure out what the y would be to get dots. What we'll do is we'll say, well, it's about y equals 3x plus 1. Because we can graph that pretty easily. But it's an approximate because I'm basically dismissing this remainder. All right. What I need to do then is to go, all right, I'm going to put a dot at the location of 0, 1, because that's the y-intercept, right? And then I'm going to go up 3 to the right 1 because of this slope from the location of the intercept. So back to our graph here. Make sure that this lines up correctly. Here's what we had established. Right? We had a vertical asymptote at the location of +1 for the x value. Now, to get the slant, I'm going to draw what would normally be a diagonal line. I'm just going to make it dashed. So if it's 0, 1, here's 0, 1 would be here. And then from that location, I got to go up 3 to the right 1 because of this slope. So from here, up 3, 1, 2, 3, over to the right 1, I'm going to put a dot there. I'm not going to make this solid though. What I'm going to do is just sort of lightly connect these two dots to make a diagonal slanted slope. Dashed, like that. Okay. Now what does that mean? I really should try to do some extra test points in this interval from here to here and from here to here. But basically the whole point of this exercise, this particular problem, is just to get you acclimated to doing something other than horizontal. Anyhow, this is what the graph would look like. You'd have one of those sort of curves, but it would be fitted in this region, right, between these two dashed lines. And then you'd have another one over here, like this. And that would be your picture, right? To really figure out where this maximum would be and where that minimum would be, I really should do this a little bit more brute force. You know, put in some test points and look for a change. You know, do the calculation, the brute force calculation. But you do have a calculator, so let's enter this, and you'll see right, that this is correct. I'm going to clear this out and enter the original thing. The whole top in its own parentheses, 3x squared minus 2x plus 1. That's the whole top. Close parentheses, division, put in a second parentheses. Right. X minus 1. Right. Now to hit graph, I may have to adjust the screen dimensions, so we'll see. Yeah, because I screwed it up from last time, so let me just fix this. Right. I'm going to go to zoom, hit Z standard 6, and there you see it. It's slanted. Right. Let me see zoom fit if that really works better. Zoom fit might be better. It's okay. You can see that there's a slant this way. Okay. if I want a more precise graph, all right, I would, as I mentioned, I would have to do some test points in here and do the brute force calculation. So let's try something like that now. Let us see. All right. Let me point to this handout. All right. If you want to sketch a more precise rational function, all right, this is the order in which I would attempt that. All right. We're going to go with what we had done when we were looking for domain anyhow, which is to factor everything, the top and the bottom, then look for holes. Right, and then look for the vertical asymptote, the horizontal or slant asymptote, and then the intercepts. All right, and we'll see how far we can get just going that far. If you just doing that, if you want to get an even more precise graph, right, you need to generate some additional points. But you can only really judge how to do that having sketched something to begin with. I made a table to sort of give you an idea. That's this page. Right, this is if you're looking for test points. You have to figure out an interval first, right? And then choose an x value that would fit in that interval. Plug it in, do the calculation by hand, and then you have a dot. All right. Anyhow, let's follow this basic set of procedures, right, from top to bottom. So if we're going to sketch, again, you would have a calculator. I'm just making you do this, you know, for the sake of grasping the material a little bit better. If you have this function, x sitting on top of x squared minus x plus, minus 2. I'm probably going to need to erase a lot of stuff, but I'll try to confine myself at first. All right. If I'm following step 1 on that sheet, all right, then I would factor these, the numerator and the denominator. The top one is just going to be x. All right. The bottom being a trinomial, that is a basic trinomial. You could probably figure out by tinkering with it without having to explore any complicated methods. If it's x squared, it's probably going to be x and x. If it's just 2 here, it's probably going to be 2 and 1. And then we'll just make sure that the signs produce a negative 1 here in the middle. You need to have a negative 2 and a positive 1 to accomplish that. Right? That's completely factored. Number 2, let's look for holes. Are there any removable discontinuities? All right. Nothing cancels. Because there aren't like factors above and below. So there's no holes in this case. Number 3, let's just pay attention to the denominator. The denominator factors set equal to 0, not equal. All right, this will tell us the vertical asymptote. So we have, this is the denominator in factored form, x plus 1, x minus 2. X plus 1 can't be equal to 0. X minus 2 can't be equal to 0 because it's the denominator. If you solve each of these two things independently, what do you get? Minus 1, minus 1. X cannot equal negative 1. That's the vertical asymptote. In this case, you would add 2 and add 2. And x cannot equal positive 2. This is a second vertical asymptote. Right, so I'm going to start drawing now, because I have two lines already. Dash lines, and so be it. That's not right. Better. Okay, so what's not allowed? X negative 1, x positive 2. This dashed line, I'm going to make it green. Nah, make it red. It's forbidden. Okay. X negative 1 is a vertical asymptote. And there's a second one at x positive 2. This is going to be an interesting graph, you can tell already, because you have two vertical asymptotes as opposed to just one. This is x not equal to positive 2. Okay. All right, let's look for the horizontal one. Let's see, step 4 here. We need the 3 rules for the horizontal asymptote. The degree of the top polynomial is 1. The degree of the bottom polynomial is 2. So the top degree is apparently less than the bottom degree, which is more or less, I don't want to say it's a normal situation, but consider our 3 rules. What is true when we have that situation, as we do? Just to summarize, when the top is less than the bottom, we have more or less the normal asymptote at the x-axis, so y equals 0. The horizontal is the x-axis. Y equals 0. So, fill that in. Use red again. This is overkill, but should run along the x-axis like so. Horizontal asymptote. This is a vertical asymptote. This is a second vertical asymptote. I may end up having to erase those, but at least it's clearly defined, right? Alright, no slant in this case, but look what we have. We have 6 spaces, if you will, 6 regions. We have most of quadrant 1 here, kind of in between quadrant 1 and 2, quadrant 2 mostly, quadrant 3 mostly, again down here and then down here. So we have quite a few intervals to look for, right, if we want to get a very precise picture by hand. All right. Moving on. Let's look for the intercepts because those are super easy now, right? X-intercepts. Alright, this is when we stick 0 in place of y. All right. If it is a function of x, then that's really y equals this. So if we stick a 0 in place of y, look what happens. You end up with this instead. I'm going to use the factored form of this because it's just going to be more convenient. You could use the original trinomial, it's not going to hurt it, but Watch what happens. If you, in a rational function, substitute 0 in place of y for this purpose, realistically what that means is that you only need to pay attention to the numerator. This will happen virtually every time. We just need to know what the numerator is set equal to 0. Right? How come? Because if you were going to solve this as if it were a regular ordinary equation, not part of a graph or anything like that, you have denominators that where the variable are. All right, pardon me, the variable is in the denominator. So you would have to move that. Right? How would you move it? By taking this entire chunk and multiplying it on this side for the sake of cancellation. And then remember, whatever you do to one side of an equation, you're obligated, your hands are tied, you have to do it to the other side. So what's going to happen though when you do that? 100% of the time. What's 0 times anything? This cancels this, right? These bottom factors for the sake of moving over equals. But if I do it here, what's 0 times anything anyway? 0. So realistically, it's this. It's 0 is equal to the numerator. If 0 is equal to the numerator, then in this case, since it's just a say only x here, that's what x is. X is 0. There's nothing else to it. You may have a problem that's more complicated than x1, and then in which case you're going to do something similar to the denominator scenario. Right? But in this case, it's just x equals 0. So, what is that in the style of a coordinate or ordered pair? Right? The x-intercept is 0 when y is 0, because that's what I used for y. So, I'm going to put a dot at the origin. There should be a dot right here because that is definitely a point, right, at the origin. 0, 0. I'm a little reluctant to write that, but I'll do it anyway. Right. We need more points, right? Let's do a y-intercept. Well, the y-intercept would really be kind of pointless in this scenario because how come? We already have the origin involved here, and that is a y-intercept. But let's just check. All right, here's 6. All right, when you're looking for the y-intercept, it's almost the same process. You're sticking 0, but you're doing it in places of x's instead. So I need the space. I'll just do the work here. If this is y equals, and this is the factored form, and I stick a 0 here, and here, and here, what is going to happen in this particular problem is that you have a 0 above the line, because that was the only thing there. And this would be 1 times negative 2. And even though that would reduce to 0 over negative 2, what is 0 divided by almost anything? The exception of 0 itself, it would be 0. So your y-intercept would not coincidentally be the origin of 0, 0. Now, here is a reason why you would want to take the time to generate more points. Right now, this is all we have. Which is not too much. I have one dot for sure, right? Because of the x-intercept and the y-intercept. But I'm not really sure where the curves are. Right? Here's where the intervals have to be decided. I'm going to put this in green very faintly. We realistically need a point here, and maybe 2 points here, and then a point here, you know. In this interval, maybe 2 in this one, and then 1 in this one, vertically. I'm sort of gesturing like this on purpose. What is the interval running from here up to this barrier? I'm going to sort of write it along, I don't really want to write it along the x-axis because the points are probably close to it. But if you read the increments of this, this is headed towards negative infinity, right? If you come to a screeching halt, right, at this first red barrier, what is that point? It's -1, right? This is -1. So on this table that I have to generate additional points, right, let us, just for reference, say that that's the first interval here. I'm going to try to sketch it. I'll have to keep moving this back and forth just because of the nature of our board here. But let me sort of illustrate filling in this table for this purpose. We have an interval. Realistically, look at the way that I illustrated this on the sheet. It's just to signify that this is an interval. I broke it up into two pieces separated by a comma, and I put a bracket here. Again, just to distinguish it from what is normally an ordered pair. Realistically, there would be a parentheses here and a parentheses here, not a bracket. I was just trying to make it distinct. You have an interval, and then some x values. And then you're going to substitute the x value into the function to figure out what y is. And then you're going to get an ordered pair from that. Now it will be unique to the problem, but the first interval would be, we're going to be looking for test points in this interval from -infinity up to -1. Okay. How come? Because that is basically this situation here. You have x values that run from -infinity up to screeching halt at the location of this vertical asymptote, -1. What is the interval after that? I would say, just for the sake of fleshing out the picture as best as you can, don't just go from here to here, right? Go from here to there. So this little narrow window, if you will, from where you left off, -1 up to the y-axis, so x is 0. And then from 0 to this additional vertical asymptote, +2, and then beyond it this way to +infinity. So we have 4 windows of opportunity, if you will. Okay? These are the intervals. They're not part of the picture. But I want you to think about it sort of horizontally. I'm just trying not to run along the x-axis because I'm going to have a lot of dots in the way. All right. So, what does that mean? It means first interval is from -infinity to -1. The second one is picking up at -1 and going to 0. The third one potentially would be from picking up from 0 going to +2. And then a fourth one would be picking up from +2 and running into +infinity. Again, this really depends on the problem at hand. Right. Now, having decided what the windows are, the frames, of x values, I'm going to choose a value for x that I'm going to use as an input. Don't use the asymptote because you know it doesn't work. Right? I already figured out the asymptotes anyway. If I go back and look at this now, if this is -1 and you already know that that's forbidden territory, right? What is the next easiest number after -1 headed this way? In that interval, -2, right? in between -1 and 0 is -1/2, right? After 0 is +1, right? And beyond this barrier of +2, the next easiest one is +3. So I would use specifically those 4 test points to flesh out the graph. So in this interval, I want to use -2. In this interval, I want to use what narrowly fits in between, which is unfortunately a fraction, but so be it, -1/2. 0, I'm going to use +1. And then beyond 2, I'm going to use +3. There's varying degrees of difficulty since we have a rational expression. But what you would do in each of these cases is plug in those x values. It might be easier to do it in the factored form. It might be easier to not do it in the factored form. Let's test it out. All right, this is x. Maybe the factored form would be easy. I'm going to just try it in the first one. All right, if I stuck an x value of -2 in the factored form of the function, that would put a -2 here, a -2 here, and a -2 there. Right? Which means you definitely have -2 on top. In the bottom, you'd have -1 from -2 plus 1. And the second factor would be -4. Right? -1 times -4 is +4. If you reduce this, you would end up with -1/2. Right? Which means your ordered pair would be -2, -1/2. Right? So I'm going to put that one dot just for the satisfaction in the picture. That is coming into resolution slowly but surely. Okay. At -2, the y value would be -1/2. It's going to be very faint, unfortunately, because of the smallness of these increments here. I don't want that to be off too much. This is -2x. This is +1. This is -1. What does that mean for us? It means that in between -1 and 0, we would have a dot here. And since this is all that I've looked for in this interval, and we already have our asymptotes in place, that means that we're dealing with quadrant 3, not quadrant 2, for this curve. One could estimate reasonably that this is where the rational function rounds out. Right? It's bounded by this horizontal asymptote, touches that point we just calculated, and then because there's a vertical asymptote that runs this way, right, this is the extent of it. Right? It's in quadrant 3, not in quadrant 2, right? Using these asymptotes. Okay, now we're going to go in that little tiny little narrow window there. In this realm, this is a little bit more complicated because we're going to end up with a complex fraction. Right? If, again, maybe I try to finagle this with the factors, it might be easier, maybe not. Let me see. I'm going to stick with the original version of this, which is x squared minus x minus 2. This would probably be the most challenging calculation because of the input being a fraction. So you would have -1/2 above the line. And then you'd have -1/2 being squared, -1/2 inserted in here. All right, straighten out the bottom first. If you square negative 1/2, what you're going to get is a positive 1/4. If you have a double negative for the middle term here, you're going to get positive 1/2. And then you have negative 2. All right. Combine the fractions because they're on the left side here. 1/4 plus 1/2 is really 3/4. If you want to combine it with a whole number, you would have to upgrade 2/1 to something with a common denominator. So let's just say that it would be 8/4. 8/4 is really the same amount as 2, right? Because what's 8 divided by 4? 2, and it happens to be a negative. If this is a positive 3, and that's a negative 8, that's going to reduce this to a negative 5/4. Now you have that on the top, negative 1/2, divided by negative 5/4. This is really what you're doing. Now from arithmetic, you may or may not remember, you keep, change, flip. You keep the fraction negative 1/2, you make this multiplication instead of division, and then you compensate by multiplying by the reciprocal, which is just flipping it upside down. You have negative 4/5. All right, and then do some simplifying, or just do brute force top times top and bottom times bottom. This would be simplified like so. Right? Realistically, what does that mean? It means a negative times a negative is a positive. 2 is the top and 5 is the bottom. Right? You have a point of negative 1/2 and positive 2/5, which is awful, all right? But it's a legit point, all right? So I'm going to put a dot at that location. It's awful because of the minuteness of it, right? It's a point that would fit in this window. If this is negative 1/2, it would have to figure somewhere halfway between 0 and negative 1, negative 1/2. 2/5 is not even the whole way down, right? It's like, a portion of the way. So I'm going to put a dot like this here, ever so slightly. I have a teeny tiny little dot here, okay? Now I need to figure out a point in this window. Hopefully that will be a little bit easier. Let us see. It's a whole number, so I'm going to go with the factor form of this. So if I insert 1 here, 1 here, and 1 here, that's a 1 on top. This is 2 times negative 1, which is negative 2. That means that the point is positive 1, negative 1/2. Still kind of yucky, but it's doable. So I'm going to put a point there. Okay. Positive 1 is this increment right here. 1/2 would be down slightly, right? I think my sign is off. Let me just verify that. No, it's correct. The other one. It was the other one, sorry. Positive 2/5. I should have put the dot above the 1. Sorry. There's a dot here. Positive 1 is negative 1/2. So I'm going to erase this. Positive 1, negative 1/2 would be here. Okay. Now we have everything. Remember that this crosses the axis. So we have this sort of almost cubic style curve that runs in these two, between these two vertical asymptotes. And it does go through the x-axis at this location. Okay? Because we generated that point and approved it, and we did that point. One more. Right? We'll figure out whether it's going to be exclusively in quadrant 1 or 4. Let us see. Using the test point of 3. I'm gonna use this factored form as it's just easier for whole numbers, I think. So debatable, but nonetheless. Put a 3 in here, 3 in here, 3 in here. This is a 3 on top. This is 4. This is 1. So this is 3/4. All right. So at the location of positive 3, 3/4, I'm going to put my last dot. Here's positive 3, 3/4 is not quite 1. You'd have something just underneath the line of 1. And since we already have our asymptotes there, we have a curve that would look like this. It's just a little sloppy the way I drew it. Running along the asymptote that way and this way. And that means that this is in quadrant 1, not in quadrant 4. So you have something exclusively in 3, something between those, between 2 and 4, and then something exclusively 1. Right? And that would be a picture. That is, again, if you're going to do it by hand, which you're not really obligated to because you have a calculator, of course, but to do it by hand, at least even one time, you know, you have a greater depth of understanding now than if you just made a machine do it. Okay. Erase this. Hopefully that reinforces the concept of intervals as well. There's a practical reason for it. You're drawing a picture. I have to be honest with you, when I was in high school, I really never would have thought I would end up being a math teacher of any sort. What really appealed to me was that I figured, oh, I could draw stuff. That was interesting to me. All right. Now, let us say that you had to write a rational function. You've sketched one, you can certainly use your calculator, but there's a model for this, right? If you had to write a rational function, we need a model. Right? It is going to bear some similarity to the polynomials model, because what is a rational function but a polynomial stacked on a polynomial? So it will look like this. In factored form is really the easiest way to have this. There'll be some kind of a vertical stretch factor, so we'll just call it A. Right? And then to be very general, there will be these terms. Like so. So you'll have an x value and an x value and then an x value. And then the first 0, the second 0, and then a 0 into whatever, how many you need. There will simultaneously be a multiplicity that you have to consider. So to generalize this on multiplicity, you could see that this looks like the polynomial model. How we make it rational? Put a line in it. And basically duplicate most of the same features, at least the factors. To make them distinct, because they do have different jobs, remember. All right, the model is often, they'll use a different letter. I mean, it will still be x's, right? But instead of putting an x down here, because they're not going to be zeros per se, right, they will use a different letter. So a lot of times they use a v. So v1, v the second, v to the n, maybe, something like that. And then an exponent as well, so we'll put a q in here instead of a p, q2, go to the m, like that. Anyway. So, what to think about when you're trying to, you start with the skeleton, all right, and then you look for those features to insert them and flesh out the skeleton. All right, now I'm not drawing a picture per se, but we all going to basically fill in this model here. All right, First thing, all right, remember the numerator factors, and I'm going to try to, emphasize that they're factors by putting them in a parentheses, all right, are the x-intercepts. All right, so we're going to basically be, if you have a drawing given to you, we're going to be looking for x1, x2, whatever. And then sticking those numbers here, here, and here. Just remember that they're counterintuitive because of the sign. The denominator factors which again I'm implying by putting them in parentheses here, are going to be what? Instead of maybe putting this in black, let me just put this in red to make it obvious. X-intercepts. These are the vertical asymptotes. Or technically the holes, not the vertical asymptotes. As for the exponents p and the exponents q. Let me just complete this thought too, since I'm kind of jumping the gun here. This is v1, v2, whatever. Powers p and q, right, can be determined from behavior. Local behavior. Now just to remind you, if the graph that you are given, and I'm going to draw a picture for you in a moment, appears to have some kind of a bounce, if the graph bounces, right, that means that your factor should be even. Okay. And if it crosses, then it's odd. I'll move the camera in a moment. Now usually what that means is you're going to use the number 2 or you're going to use the number 1. Right? Because it's a rational function, I'm going to give you one other piece of information. 2 and 1 is what you use. 1 for odd and 2 for even. But let me get there when I get there. Okay. The A value, let me just squeak this in because I'm trying to build an overview here, and then I'll give you an example. For the A, use the Y-intercept. You could use any number that's not an X-intercept or an asymptote, right? But for the A, all right, plug in Y-intercept coordinates. All right. That's the best course of action. You could use some other point, but I would go with the y-intercept, right, if there is one. Or something not x-intercept, right, or an asymptote, of course. Y-intercept would be the easiest thing. Here is the last piece of sort of preliminary information that you might find useful as a reference. Right. I'm going to erase something over here. Okay, we have a model, we have the pieces and how we're going to fill them in, including the A. Right. As a reference, just remember a couple of things. If you had the function that is 1 over x to the first, right, this is how the graph looks. Like that. If you had the next most complicated version of this, which would be the function, but changing the degree. So x squared as opposed to x to the 1. Your function would look like this instead. Right. What is important to note from these two things? Is the direction of these two arrows. These head off into opposite infinities, if you will. These head off into the same infinity. The verticals, anyhow. Right. It doesn't necessarily have to be the same that they're both positive. This is out of the frame, sorry. But remember this, right, because it's going to be useful in a moment. Right? Your verticals, arrows, if you will, head off into opposite infinities, one positive and one negative, right? When you have the x, the standard reciprocal function. If you just change it at 1 degree higher, they're going to end up going off into the same infinity. If there is some negative, factor in the front, it would just be vertically reflected, but then they'd just still be headed off in the same infinity. It just would be negative instead. Okay? Remember those two things. Okay, I'm going to save this model, and now I'm going to draw a picture on the graph that I have. And we'll slowly fill this in. I have to, unfortunately, duplicate my example from what I have drawn in my book here. But bear with me. Oops. My ledge is just not wide enough. Okay. So imagine that you are given, this is an example, this drawing. Falling off again. Kill me, please. That's pretty well defined, I think. All right. Suppose you had nothing given to you more than that there is a dot here at 2, negative 2, and something along the y-axis here, and then another one over here. 1, 2, 3. And you had curves that look like this. Put them in blue. from this, you could, believe it or not, write an equation. So you have some key features. In fact, they wouldn't even have to, I'm purposely making these red because I want to zero in on them, right? Notice that there are no asymptotes really drawn here. You could kind of guess where they are, but I'll hold off on that for just a moment. One thing you want to notice, if it's touching the x-axis, the points that are in red, right? If it's touching an x-axis, this would logically have to be an x-intercept, and this would be a second x-intercept. So since we need those to fill in the top of our function model, let's figure out what that location is. What is the x value at this location if you estimated it in reference to 0, 0 here? -2, 0 in that respect. This one, probably +3, 0. Right? If you took those and then, somewhat counterintuitively, wrote them in the style, instead of not an ordered pair, but wrote them in the style of a factor, we could start to flesh out our model. It would be x and then something and then x and then something. If it's -2, what would it have to be in the factor, counterintuitively? +2, right? And in this case, if it's +3, what would it be counterintuitively? -3. So I'm going to take those two things and insert them in the model. Okay. So we have this much. X + 2 and x - 3. This is still a function, of course, set equal to this stuff. Okay. Thankfully, what that means is I don't need any additional terms, so I'm just going to ditch that. Okay. All right. Now let's try to decide what the powers of p would be, the exponents, right, based upon behavior. Remember, we're going to decide based upon multiplicity, right? If there's a bounce in the graph, that is, it touches the x-axis and moves off of it, doesn't go through it, it bounces, then the factor would be even. Right? If the factor, if at that point in the graph, that 0, right, crosses the x-axis, it goes through it, penetrates it, then we're going to make it look something linear, so it's probably going to be 1. Usually, since we're dealing with factors anyway, it's either going to be 1 or 2. Right. Odd or even. Linear or something that's not linear. All right. At this location, again, we're trying to figure out what p is and what p is. It crosses through the axis. This is a cross. So therefore it has to be odd, right? In its most simplest form, since it appears to be linear, if it's crossing, right, then this is a 1 at that point. The same thing could be said for this other x-intercept. It crosses the x-axis. So we're dealing with something that is odd. Right? And the most simplest version of an odd is a 1. It's linear. I know that this is a big curve here, but at that point, it's linear. So we're going to pretend that this is 1. Okay? If they're both 1, you really don't have to write them. But just to say that we covered that base here, I'm going to put a 1 here and a 1 here. Now we need to consider the denominator factors, which would be the vertical asymptotes. Okay. It's a little faint, all right, because this is a rough sketch. All right, but you could probably infer, deduce what the the x-intercepts are. I'm going to draw them in red, unfortunately, just not to confuse them with the axes. It seems that the curve is running alongside a vertical asymptote here. What is the location of this vertical asymptote? Looks like it's x not allowed to be equal to -1. Save that. All right, and in this case, it looks like there's a vertical asymptote that this graph, the two halves of it here, are running through this way. At this location would be x not equal to +2. Save that. All right, now again, we have to disguise these things to look like factors. Right? So if I made them a factor, if it was x -1, it's counterintuitive, right? In the style of a factor, this would be x + 1, right? And in this instance, the factor, counterintuitively again, would be x - 2. All right, so I'm going to take these two factors for the vertical asymptotes. This is a vertical asymptote, and this is another one. And insert them in the model. X + 1, x - 2. And that means I don't need the additional features here, so I'll just erase that. Okay, now we need to figure out what the exponents would be, and we're going to again examine behavior at those locations. All right. That's why we need these two references here, because of this rational situation. Okay. Let us analyze what these vertical arrows are doing, right? And we're going to see at the point of the vertical asymptotes, right? That vertical asymptote first, and then that vertical asymptote second. Whether we have arrows headed off in opposite directions vertically, or if we have arrows headed off somehow in the same infinity. Okay. Now look at it in this case. You have right? We have an arrow headed off in positive infinity vertically, and along the same red dashed line, we have an arrow headed off into negative infinity. So these are opposite, which means that if we were choosing a q for the power in this case, and a q in this case, all right, this one at x - 1, the factor x + 1, that style, would probably be most similar to the situation where we have something that behaves like x1. Right? So we're going to put a 1 in that case. All right. When you go over to the second factor, that is a vertical asymptote, the x - 2, that is through +2 here. Notice the direction of the arrows. Right? This half runs along the axis down, and this one coincidentally does the same thing. Now granted, it is upside down, but if you had to hazard a guess, which of these two things does it most closely resemble? The x1 situation or the x2 situation? I would say, and I'm sorry if this is out of the frame, I'll just pitch it slightly. This most closely resembles where you have, they headed off into the same infinity. It just happens that they're upside down. So, since this is bearing some similarity to the x2 situation, right, headed off into the same infinity down, I'm going to go ahead and say that's probably 2. Right. So the x1 factor is 1, the x minus 2 factor is squared. Let's put this out of the way. So we have 1 for that one, which is superfluous. You don't have to put 1s really. You're just filling it in to make sure that we covered all bases here. And this one is probably going to be a 2. All right. That means the only thing left over to do is to look for the A. I'm sorry, I've kind of erased the instruction here. The sun is finally coming out. The sun will come out tomorrow. Bet you weren't expecting that tomorrow. Okay. Shut up, Ziegler. Get busy. All right. It's so nice to finally see the sun again. All right. We really only need to find the vertical stretch factor A at this point. And again, it's not, you don't have to do this exclusively, but if you're going to find A, then realistically try to plug in the Y-intercept. Why the Y-intercept? Because it is not itself an X-intercept. We can't use X-intercepts or vertical asymptotes. Right? They're already part of this. Right? And it just happens to use small numbers, right? You know, what is the X value of a Y-intercept logically? 0, right? So super easy to use. So let me erase what is unnecessary at this point. And insert what we can, right? If the function is really standing in place of y, right, and we're going to in fact use a y-intercept, we know that it's for the x value, it's going to logically be 0 for x's, right? Let's look at the picture and see if we have a y-intercept. I'll really confirm or deny whether we're going to use it, all right? We do, right? This dot that is here is a y-intercept because it's riding along, it's on the y-axis. So if this is a y-int, let's read its location. It's 0 logically for x, and it's down 2, so it's minus 2. I'm going to use 0, negative 2 in the function to figure out what a is. 0, negative 2. So, in place of y, I would have no choice. I would have to put negative 2 here. And in place of all of the x's, 0, 0, 0, 0. Super easy to use, right? That means that this is going to reduce by a lot. All right? I'm going to have negative 2 equals, realistically it's a, sorry, because that's what we're looking for. I'm going to have 2 and negative 3. And on the bottom we're going to have 1 and negative 2 squared. Alright. So simplify, and then that's to perform arithmetic here, and then perform algebra second. This is going to be squared, so this is going to be 1 really times 4 on the bottom. And on the top, this is going to be negative 6. So that means we have negative 2 is equal to, I'm going to be a good guy and put the negative 6 in the front of the variable. Negative 6, that is more aesthetically pleasing and it's better etiquette. And this is sitting on top of 1 times 4 is 4. You could do this a number of different ways. You could reduce this as a fraction to 3 over 2. then multiply by the reciprocal both sides. That's usually what they would tell you to do. But even if you didn't, all right, let's say that you just wanted to get it done. All right, move the 4 times 4 times 4. This is now negative 8 is equal to negative 6a. All right, do it in 2 steps versus 1. All right, divide by negative 6. Divide by negative 6. The negatives are going to cancel. A is equal to 8 over 6, which if you reduced it by its GCF is to divide by 2, divide by 2. It would be 4 over 3. Okay. That means that this is what your function is. It's long, it's complicated, it's rational. Right? But in place of A, it's 4/3. That's the vertical stretch or compression. It's going to be a stretch in this case. And I'll just fix this. X, 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 X. Now, since these are 1s, they're superfluous. You don't need them. I'm just going to make this as simplified as possible. I'm going to type this into my calculator to confirm that it is correct and that it most closely resembles the picture that we have originally. All right, again, be very anal retentive about how you type in the parentheses. You want to make sure that it doesn't accidentally confuse parts. So it's a little tedious. All right, what I would do is start with this. Let's put things in the intuitive way for the red stretch factor here. All right, I'm going to put it in n/d to make it an intuitive top and bottom. Here's 4, here's 3. All right, now I'm out of that. I'm going to put my first, you could actually do this again, all right? I'm daring, so I'm going to go ahead and do that. I'm going to choose that same function again. No, it's fighting with me. Sorry. Don't do things backwards if you can avoid it. It makes it more complicated. I'm going to put a parentheses here and see if I can get away with doing it in the intuitive way. It's not wrong if you put all of this in a lot of parentheses, but I find that people tend to make syntax errors when they do that. So I'm going to be very careful. All right. There's my fraction inside of its own parentheses. There is a top and a bottom, all right? X plus 2 sitting next to x minus 3. And on the bottom, x plus 1 sitting next to x minus 2, and I'm going to square that. All right, now here's how it looks typed in the fancy way. All right, let's verify what's written here. X plus 2 sitting next to x minus 3. On the bottom, x plus 1 sitting next to x minus 2 squared. There's a little 2 here. Now, assuming that all is going to go according to plan, I'm just going to scoot over to see the 4/3 here. There's a lot of parentheses here, but this is pretty much how you would write it, right? Rather than how you would type it or enter it. Now, I'm going to hit enter. If I have to, I will adjust the screen. Yeah, it looks like I'm going to have to adjust the screen. Okay, let me put this in automatic here, Z standard 6. My hands are so dirty. If it takes too long, it means that it's befuddled. So you have to turn it off. For a complex function like this, it's not surprising that it's kind of goofing. All right, off. Now it tried. All right, turn it back on. Graph. There you go. Now let's go get the other picture. Here's the original drawing. There's a lot of gobbledygook, so I'll erase some of it. Should have something that looks like this. Let's see. Yes, that appears to resemble it. Notice that it's dipping below the x-axis here and it's just scooting above it. You didn't really have to look for the horizontal axes, horizontal asymptotes in this case. Right? The model, because it's factored, is sufficient. Right? Now, if you want to, you could test some of these coordinates. Right? All right. Second, well, not that second. If you hit trace, all right, plug in some values. If it's already set to 0 here, you notice that the y-intercept is -2, as it's supposed to be here, right? These other 2 points are x-intercepts, which are very faint right now. But you can put in what we predicted, -2 for the x value. It should be 0 for y. And there you see it. There it is. And then that one is +3. And you see it is also a y x-intercept, it's y0. Isn't that cool? Yeah, I think so. Yeah. All right, we're done, right, with chapter 5. Right? It's kind of a lot, which is why I have these handouts. Definitely print this, you would want that. And I think this summarizes nicely the procedure. Right? Even if you're not going to graph by hand, I would have that at the ready. Right? Okay. All right, as for homework, let me erase this. You just have to do section 5-6 now, and you have a week. Okay. Do remember to vote also, because it's election Tuesday, next Tuesday. Okay. It's just section 5-6 practice. And it would reasonably do, since today is Thursday, it would be due next Thursday morning. Okay? Alright, thank you guys for sticking with me. Be careful out there, don't forget to vote.